Well, good day. Today's presentation is on sustainability in the built environment. As architects, I'm sure you already realise that the way we look at that is to break it down into these fundamental categories of embodied and operational energy. Embodied energy meaning the energy required to construct the buildings in the first place, materials that are delivered, where they come from, the construction process, and so on and so forth. The operational energy being the energy that the building uses during its lifetime. And the lifetime of the building is something that we really do need to consider. And I might talk about that a little bit later on in the presentation. Roughly speaking, we could say 50-50, given an average life of the building, between the embodied and operational energy. This year, for your first year of your master's course, we are particularly interested in your explorations of the embodied energy of the building. Next year, in your final year, you will be having to look at both of these issues, in fact, but I don't think it hurts to flag up the overall sustainability of your project at this stage. As I mentioned earlier, just now, materials, of course, are a huge part of this whole exercise, and so there's a few points that I wanted to make early on in this process. As it says in front of you, that you think of building sand as perhaps sand that you can find anywhere in the Sahara Desert or on your local beach, but in fact it isn't. It is a particular type of sand. It's sharp sand. It hasn't been eroded and rounded by hundreds and thousands of years of either water or wind activity, and it is in short supply. At least the obvious sources of it throughout the world are in short supply. Cement, and I think you're probably already aware of this, people always say that using concrete and using mortar is a problem nowadays in terms of its impact on the climate crisis. The reason is, yes, it accounts for a huge proportion of the world's carbon emissions, but specifically, as it says there, that there are two parts to the process. It's the cement in the concrete and in the mortar that's critical, and there are two parts to the process, and one is the chemical reaction of the limestone or chalk itself when you're manufacturing the cement, and the other is, of course, the energy that you need to heat the kilns to burn it. The latter is something that we are starting to work on, and you can control, because the energy source for that can be mitigated to some extent. There are still a lot of conversations going on about how it's possible to mitigate against the chemical reaction. That's a far more difficult thing to deal with. So, of course, the industry is looking to alternatives to cement as the binder in these pourable materials, if you like. And just the final one, I just wonder how many of us have heard of niobium. I hadn't until recently, and it's an element that apparently is crucial to the steel that we use for reinforcing, for tensile structures, cable stay structures, and so on and so forth. And it all comes from most of it comes from a single source. So we have to be very careful with how we use the world's natural resources. So the primary aim of this lecture is to emphasize, or to get you to think about how you can, in the way you design buildings and the way you design the structure of buildings in particular, how you can optimize and minimize their embodied energy. So I'm going to give some kind of general classifications of how it could be done. The very beginnings of your thinking about putting a building together must involve its skeletal frame, its structure. How are you going to do it? And I mentioned just now what we're looking at here is on the left-hand side is the Clifton Suspension Bridge, the first suspension bridge in the world, which is using elements that are in pure tension. Now, the moment you are using elements in pure tension, you're already minimizing the mass of the structure, you're becoming structurally efficient. So, one thing to look at is, can you use elements in pure tension in the way you put buildings together? The second image is, I can't remember, and I'm sorry to embarrass myself, it's Felix Candela or Heinz Isler. Anyway, a thin shell concrete structure. At the time when these beautiful structures were being developed, structural engineers and architects were looking at the efficiency of three-dimensional geometry, and using that three-dimensional geometry to make envelopes, to make efficient structures. So we'll look a little more about that in a moment. The third one, of course, is someone might notice, it's Friotto's experiments with soap film structures to develop his tensile fabric structures. He was looking for, and it's known in physics that if you allow soap film to find its natural form, for example by dipping wire into it, it will make a minimal surface. It will optimize always. So these are, again, the most efficient minimal surfaces that you can achieve. That's what Friotto was looking at. And the final image is a tensegrity structure, which, if you don't know, was invented by Buckminster Fuller jointly with Kenneth Snelson. This is one of Snelson's sculptures, and again, the very minimal use of materials to develop structural form. In this case, the compressive and tensile, the compressive elements do not even touch each other, which is a real piece of structural wizardry or gymnastics, if you like. The other way we can possibly minimise the amount of material and the amount of the way we go about putting buildings together is to optimize the actual wastage in the construction process. Okay. Again, what we're looking at on the left here is early self-build project by the Swiss architect Walter Siegel, in the middle of the last century. Walter designed this wonderful blueprint, effectively, so that people could put buildings together with, again, minimising the amount of wet trades involved. So it was about also making it easy for self-builders, but also his blueprints involved the kind of materials that you can obtain at your local builders merchants, and the minimum amount of cutting and therefore wastage. So if it was a 3 metre long piece of timber, what you would do with it, at least you would cut it into two halves. There were no offcuts, if you like. Try to minimise the amount of offcuts, therefore minimise the amount of wastage on site. The middle image is the beginnings of system building by Fritz Haller. And again, there's a separate lecture which we will give on building systems later on in the season. But again, this is Fritz Haller. And his designs, again, were using the structural components, the steel components, by designing them in a very light and efficient way, and making assembly, on-site assembly, efficient and fast. And the third one is these extraordinary domes designed by Dante Bini. Bini shells, they were called. Dante Bini invented a new way of casting concrete by inflating them in using pneumatics, rather than building huge timber formwork. He basically inflated the concrete dome. So that, again, incredibly efficient way of looking at putting structures together. The actual process of fabrication, of course, can also be made efficient, and is. You've probably seen the image on the left before of what we do to your average tree trunk to maximise the kind of timber sections that we can get from it. Every tiny part of it is used. The middle section is the middle image, beg your pardon, is laser cutting steel. And again, this is something that fabricators have been doing for a long time. They will optimise the kind of cuts that they get from a particular roll or sheet of steel. They will always look to to be efficient and to minimise the amount of offcuts. So there are actually computer programs that they will use to do that. Imagine you have to cut a series of circles out of something. You don't want the interstitial spaces to be wasted. So fabricators are always looking at that. The image on the right is, again, some of you will recognise, it's the British Museum. It's Norman Foster's roof, glass roof, and I tried to do this as quickly as possible, but the quite interesting thing about it was that it was, when they, on plan, it's pretty much, I think, like a bit like a bicycle wheel with spokes radiating, and of course it also mimics Frater soap bubbles in section, but it was all perfect in terms of the number of triangles and the sizes of triangles when they originally thought of the idea, because they had a circle in the middle of a rectangle. But when they went to measure the British Museum, they found that the circle wasn't in the middle of the rectangle, it was slightly off. And this caused a huge amount of problem, as you can imagine. And this was the beginning of the development of parametric modelling, because some clever chap at Bath University, whose name I forget, and I apologise for that, it'll come to me later, developed a program, and we actually saw it being demonstrated, whereby on plan he pulled the circle that was in the centre of the rectangle slightly off centre, and everything around started to naturally adjust itself. Now what it was doing was it was optimising to make the minimum number of sets of triangles. Okay, that was the intention, so that when it came to cutting the glass and making the metal frame for the glass, that it could be as efficient as possible, and you could use the least amount of wastage. So these are all things that we can consider when we're putting buildings together. Here's just a few examples, which is really not fair of me, but just to show what you perhaps don't need to do. Some of you might be familiar with the building at the top, which has very interesting, I think it's an offshoot of the V&A, I think I'm right in saying. Anyway, a very interesting cast concrete form initially, that is then clad in a whole series of concrete louvers that I'm not entirely sure what they're doing. Are they decoration? There's an awful lot of material there. I'm not entirely sure what it's for. The lower one, again, you might be familiar with. It's the Herzog and de Maurien's extension to the Tate Modern in South London, and not my quote, but the quote of actually one of the job architects on it, when I noticed that, again, looking at these images, how sort of simple and elegant the concrete planar frame is, if you look at the image on the left, that then is clad in an awful lot of bricks. And it wasn't my quote, as I say. You could have built quite a lot of houses with those bricks, shall we say. So, as I said to you earlier, this is something I think needs to be considered. It is your building. Is it something that you can analyse what the life that you're expecting it to be, or given that, how easy could it be repurposed or taken down and recycled, if you like? So this is again something you might start to be considering. So going back to in a little bit more detail than the things we were looking at just now, structural form, as I said to you earlier, particularly when you're looking at these kind of big cast planar systems, geometry is the key. As it says there, the arch, the simple two-dimensional arch, if you like, that has a particular geometry in relation to a gravity that over many centuries has been found to be efficient when you take sections from a cone. So there is a direct relationship between structural form and the pure geometry. In this case of a cone, you get the parabolic shapes, you get the ellipses, and you get the circles, and all of these we know are efficient when are used for arching. This diagram is in our book, Introduction to Architectural Technology, and it sort of goes through the different pure geometries from which you can develop efficient surfaces. So the top section these are known as anticlastic shapes. So you get the kind of the saddle shape, which you're probably familiar with, and the one that looks a little bit like a Pringle, and I've never really come across another description of it. The saddle shape is also known as a ruled surface. And interestingly, if you look at the diagram now, you can see that they come from if you look at the central drawings, these are catenoids, and you connect the catenoids with one of those shapes, arched shapes, and then you start joining the dots, if you like, and you will quickly develop both of those types of surface. And these three-dimensionally are very efficient. You can use any arch shape to join the circles in the catenoid. Interestingly, they can work in pure compression and they can work in pure tension. So the ones on the left, top two images on the left, are compressive shell structures, thin shell reinforced concrete, and the ones on the right are fabric. Well, the top one is fabric. The bottom one, which is the velodrome that Hopkins built for the 2012 London Olympics, is actually a beautiful. It doesn't look it, but it's actually a cable structured roof. The lower images are all what known as synclastic shapes, so they tend to curve outwards, and you can see there on the left diamatic and lamellar domes, which are both, when they were designed, well, the Houston Astrodome certainly was the biggest span, biggest spanning dome at the time. The geodesic, again, is a very efficient way of enclosing space, as is air, and as I mentioned earlier is tensegrity. These shapes were developed mainly, these the anticlastic shapes were developed, as I say, in the middle of the last century by these great architects and engineers like Heinz Isler. This image was from his studio, just showing very simply what happens when you put a simple plane into a curved section, how suddenly it will take load, whereas as a piece of card it didn't. I mentioned just now geodesics. This is Bucky Fuller's dome in Montreal. I mentioned earlier the importance of having elements in pure tension. So this is Hopkins Schlumberger Centre up in Cambridgeshire, another example. What are we looking at here? We're looking at a series of, effectively, cable-stayed bridges, aren't we? So 1, 2, 3, 4 bridges that then start tensioning fabric to form the roof. Yes, you need space beyond the building to make these kind of structures, but they are very light, therefore very efficient. Mentioned earlier the thin shell reinforced concrete. These pure geometric shapes span great distances for very little or relatively little material. More recently, I say more recently, we've come back to looking at these kinds of domes and vaults, which originally were known as a Catalan or tile vault. The reason we find that these are becoming of interest again, this is an early image, the Guastavino company, the Italian firm that went to build over in the US at the beginning of the last century. They did a lot of the subways in Manhattan, beautiful structures. But the reason we find them interesting, and this is a relatively new one, is that you're making a vault, making a big vaulted roof, but without a huge amount of timber formwork. So the principle so just go back again, the principle of the Catalan vault, the tile vault, is that all you need are the guidelines, and then you lay up, a little bit like making an igloo, you're laying up, in this case, thin clay tiles, gradually building up the structure by laying one tile onto another, and so on. So you're not using as you would in a kind of Gothic cathedral where you need a huge timber structure to carry the masonry, or even with those reinforced thin shell concrete, you still need the timber formwork. In this case, you don't. So as I said, this is a relatively recent one. was engineered by Michael Ramage from the Natural Materials Group up in Cambridge. Again, also using local materials. The other advantage of course, tile and clay is clay is still very common and easily extracted material throughout the world. So local materials to make the tiles. Not quite sure what the final cladding's all about, but there you are. Here's the similar principle. This is down in Latin America, Candela, I believe. Astonishing use of tiles and very thin reinforcing mesh. So there, just to go back again, as I mentioned earlier, there's the catenoid, and once you've got that catenoid shape, you can develop all of these very efficient thin shell structures or tensile fabric structures. Both work very well. So there is this direct relationship with the pure three-dimensional geometry and the efficient structural forms. So there's a number of ways of being efficient with structure. Don't forget again the construction process. When we give you the lecture on building systems, we'll look a little bit more about that aspect of being efficient with the actual construction process, and it's up to you this year as to how you concentrate your work. You obviously can't do everything. You might decide to work with with tensile structures, which is absolutely fine. We'll encourage it. Or you might decide to go kind of sort of Walter Siegel route and not so obsessed with the actual structural form itself, but with how you put the buildings together and whether it might be self-build or what have you. So I'll do this part fairly quickly, because I said it's not absolutely critical to you this year, but in general terms, and I'm sure you already know a great deal about this. An interesting fact, I think, that the proportion of the earth on which humans are prepared or able to live is about 4% of the surface, if you include the sea, 12% of the total land area. I think in your lifetime and in mine, this is going to have to be expanded, and we'll look a little bit about how that might happen. The image there is a rather fun one, which was some architects got hold of the Palm Island project and wondered what if it became a little bit more symbiotic with nature rather than just imposition of a human shape onto the sea, and allowed nature and water to flow naturally in relation to the to the development. But that's kind of by the by. As I said, I'm not going to go into this in great detail. I'm sure you're all very understanding of how human comfort works, and that it's the critical things of the air temperature, movement and humidity. This is just a bit of an aside that this does not mean that I'm a climate denier, by the way, because this whole lecture is about being efficient with the world's natural resources and trying to make sustainable developments. But it is interesting, and this became a lecture that we had from a gentleman from the Natural History Museum some years ago, brought this chart to us to show the periodicity of the Earth's movement around the Sun, and how over a period of, I think it's 96,000 years, it says there, regularly it morphs between a circle and an ellipse, and that is why we have ice ages. And as it says there, we will have, no, it doesn't say it there, but there will be another ice age. We don't know, between 5 or 10,000 years time there will be another one, so it will get cold again. And there he recommended that if you, for the sake of your great or however many great grandchildren it is, that you invest in property probably south of Lyon in France, because everything north of that, including where we are right now today, is going to be under ice, that's for sure. The sun is our nearest star and the centre of the solar system. That's our fuel, that's our light, it's basically everything. The image that you're looking at is an image I thought I'd do. The little blue dot is the Earth. It's, of course, it's not the relative distance between the two, but it is the relative size of the two, which I always thought might be interesting. You know, the way architects like to understand scale. Again, you will know about all altitude and azimuth already and how to plot the movement of the sun. But of course, it is absolutely critical that you do know this when you're designing for a good passive, environmentally controlled building. You've got to know where the sun is, how it works in relation to your building, and you have to know that from day one in terms of how much glass, how much light, how much heat gain or heat loss, according to where you are in the world, that you're going to control through your passive climatic envelope. So knowing the sun path is important, I think, from the very beginning. Also knowing the levels of humidity, because again, this is really, in terms of human perception of comfortable climates, the humidity is important. And so environmental engineers tend to use these psychrometric charts, looking at wherever you are in the world, and measuring the humidity against temperature, and therefore looking at what would be a natural comfort zone wherever you are exactly, and always trying to expand that by the designs of their buildings. What are we in control of as architects? We're in control of certain variables that then enable us to passively make an efficient envelope. And those variables, as you know already, I'm sure, but I'll just repeat, are thermal mass, insulation, air movement, and solar shading. I'm not going to go into these things in great detail right now. You can always look back at them. So with thermal mass, we can use thermal mass as a battery, can't we? We can use diurnal change. If you have hot days, cold nights, you can warm up your building. There's this idea of a trombe wall where people always find it strange when you say, I'm going to build a wall in front of my window, but actually it works as a battery, doesn't it? So during the hot days, that heavy, dense thermal mass will heat up and then can re-radiate that heat back into your buildings during the cold nights. Passive environmental control. Thermal labyrinths, this is now used at a large scale underneath structures to either draw cools out of them or emit heat into them. Water is thermal mass, so you can make a water wall and it'll have the same effect to some extent as heavy concrete or any other kind of dense material. Insulation, why am I showing you this? Because it was discovered many years ago that a penguin, which body temperature is about the same as ours, 30 degrees something, survives quite happily in minus 50 degrees. So it's dealing with sometimes an 80-90 degree temperature differentiation between the inside and the outside. How does it do it? Well, what they found was that it's not the feathers on the outside, and it's not blubber or fat. It is by sectioning, to go into too much detail, but they have a very, very small layer, probably about 5 millimetre, of what's known as down feathers, DOWN, and these trap microscopic bubbles of air, and it's those microscopic bubbles of air that slow down the transfer of heat, the heat from inside to the outside, from the outside to the inside in their particular case. So that's what we mimic when we design insulation. Initially, why you get these little, when you're cold, you get these, what we call in English, goosebumps. This is a hangover from when we used to have hair, because what happened, of course, initially was when you get cold, these are little muscles, tiny little muscles that would push the hairs up in your body, on the outside of your body, to trap air between the hair and your skin and therefore create a layer of insulation. We don't have hair anymore, therefore it's a kind of evolutionary hangover. And if you are interested in that kind of thing, there's a very interesting book, again, it was written back in the 1960s by Desmond Morris, about why exactly it is that of all the, I can't remember how many species of apes there are on the planet, over 300 or something, why was it that only one of them decided at some point it would be a good idea to lose all of its hair? Anyway, have a read of that, and it might help you to understand more about why we are the way we are. As I say, so having, you can have thermal mass to trap the heat. You can have insulation then to stop that heat getting away. Here's the sort of fibrous materials that we use to trap all that, to trap the air. Silver foil to reflect. Cavity walls to do the same thing. You can spray it on. This is aerogel, which is the nearest thing I suppose you could say that we have at the moment to that layer of 5mm layer of down feathers that penguins have. Very, very incredibly light and incredibly high insulating material. So then you can start to look at very thin walls in terms of insulating to a high degree, or you can go completely the opposite way and use straw bales, where you might need sort of a wall of about a metre thick to do the same, to have the same effect as that piece of aerogel, but done with a local sustainable material. This is using hydroponics for the same purpose, because of course vegetation will insulate. These are the sort of drawings that we do to show how we're mitigating heat gains and heat losses in buildings. And of course, let's not forget that the biggest culprit, shall we say, in buildings in terms of heat gains and heat loss is glass, and all the things that we do to glass to mitigate that are shown on this diagram. Of course, it's interesting now, that's only showing double glazing. Now you can get triple glaze. I think you can get up to 5 layers of glass. But of course, if you're really doing the whole life audit of a building, or if you're doing a complete audit of the energy a building uses, from the embodied energy through to the operational energy, you think about the manufacturing, delivering to site of a triple glazed section of glass. Glass is a very heavy material. The energy involved in the first place, the embodied energy in glazing a building in that way, against the amount of heat loss that it's going to mitigate through its lifetime, is a complicated calculation to make. I'm not always convinced that you might not go back to that single pane of glass. But again, knowing where the sun is important. You can now look back at buildings with thermal imaging and find out where they are leaking, where heat gains and heat losses are occurring. So this is very useful. I think finally let's just quick look at air movement and the importance of natural ventilation, both for cooling and for air exchange. Wind roses, you can get these for all parts of the world now. You can find out exactly where the prevailing wind is, wherever your site is, the speed of it, and therefore where you might want to look at where your openings are in your building to allow natural ventilation and to allow heating and cooling to occur. The importance of the stack effect, or Venturi effect, to allow to again encourage natural air movement before we start putting in air conditioning. There's nice diagrams like this that you can use to explain that in the way you're passively ventilating your buildings. There's nothing new in this. This is old techniques of using, of course, chimneys. Everyone knows that chimney will naturally draw air up through buildings. and we're still doing this today, particularly in the Far East, Middle East, beg your pardon. So that go back. In that case, it's wind passing over and through the stacks that will draw air up through the building, as long as you have openings low down. In this case, you're facing these catches or scoops towards the prevailing wind and drawing air down into the buildings. Similarly, with these cowls, as the air passes around them, air speeds up. This is, if you look at the image at the bottom right, this is how aeroplane wings are designed. Aerodynamics, in order to get lift on the wing, they're designed with those particular profiles because the air will speed up around the circular section, and therefore that naturally draws warm air up from inside. And of course, these cowls particularly can find the prevailing wind. They can move on plan, and so these are here are some designed by Bill Dunster for the Beddington development in South London, one of the early low carbon, zero emission developments in England. That he designed these beautiful, these wind cowls that had that could rotate and draw air up through natural air conditioning in the building. Evaporative cooling is another way of again using water. Anybody who knows that if you have water on your body surface and air passes over it, it naturally feels cool on that area. So that's what's happening with these wind towers that are drawing the water up. We don't often promote putting wind turbines or, if you like, trying to gain energy as part of architecture, either through wind turbines or through photovoltaics or through anything else. I mean, it doesn't seem to be necessarily part of architecture. The important thing, I think, is to be efficient with the passive envelope, with the materials that you're using, with the amount of the relationship between insulation and thermal mass, and the amount of glass, and where that glass is in relation to the sun, and so on. Nevertheless, this is a nice little project because these architects realised they had a site that had a particular shape already a little bit like an aeroplane wing, where the prevailing wind as it passed around the site, if they built a tower, which they did, would create if you like, the wind would amplify, and therefore if they put a string of, in this case, helical wind turbines on the leading edge, I'm not sure what the terminology is, anyway, they would be likely to turn more rapidly. So I think that is quite a nice use of gaining energy from the wind. Oh yes, finally then, okay, so importance of solar shading. Again, I'm sure you know about, but it's fine, in a climate where you have got low winter sun and high summer sun, it works perfectly well. You get the sun when you need it, and you don't get it when you don't need it. It's Corbusier. Brise-Soleil do the same thing. Deciduous trees do it all on their own, which is rather nice. Just here's some examples. This is actually just to remind, a little bit over the top perhaps, but these louvers controlling solar gain. Of course, in the northern hemisphere, we tend to put them horizontally facing south, vertically east and west, and none on the northern side. There's some other examples. This is a rather nice one. This is in Madrid again, I think, and it's little sort of, the whole building is ringed with these nice sort of little bamboo shading devices which can be opened and closed. Yeah, I suppose, anyway, I think this is sort of what not to do. I think this is just putting these overhangs. It's more of an architectural decoration than actually going to solve any particular overheating problem, I feel. Similarly, these building noticed in London, which has this vertical louvers all the way around it, again, which I don't think is going to do a great deal of mitigation, but is using an awful lot of material. The sun has a very particular path, and it's quite nice. This is a student project from many years ago. A colleague of mine at the AA, Manit Rastogi, started looking at exactly if he made solar shading in the shape of the sun path, that would be a kind of minimal solar shade. And then this was taken on by another student, Guy Westbrook, who designed a completely self-shading building for the tropics, so that the shading system around the outside was absolutely, used the minimum amount of material. The rule being we never let, we don't want any direct sunlight into this building. Therefore, they were sort of semicircular on plan anyway. This is pretty much bang on the equator. This is for Kuala Lumpur, I believe. So it's designing again with the sun. I think finally just to remember that, what does glass do? Glass does have this effect of heating up enormously. Hence, we've used glass houses to, for tropical plants in the northern hemisphere for many generations, and it can be used to, it can create overheating, or if we need the heat, which we probably do more in the northern hemisphere, in extremes, then we can use the greenhouse effect to our advantage. I think this is the last slide. This, I believe, this is also in our book, Introduction to Architectural Technology. It was done by environmental engineers, ex-CO2, who kindly gave us this rather nice, simple. It's the Köppen climate map. Some of you might be familiar with already, which divides the world into certain climatic zones, and then some kind of general guidelines for passively designing for each of those zones. This is not telling architects how to design, but it's giving some general hints on good passive house type zero carbon operational energy principles. So yes, thank you very much, and good night.